Well, hi there. Here's an interesting topic to discuss. The geometric configuration and the three-dimensional morphology of geological features are important in our understanding of their genesis or development and also their significance. A couple of words about myself. Uh, my name is Robert Font. I have a PhD uh, in the geological sciences from Texas A&M University. I'm a former professor of geology at Baylor University, project supervisor and area geologist at what is now ConocoPhillips, and president and owner of GVM Incorporated. I'm a certified professional geologist, as recognized both in the US and Europe, and an active member of the AIPG. Well, here's an interesting question. What geological features could be represented by the mathematical functions that I'm giving you here? Y is equal to 2 times the absolute value of x. Y is equal to x squared. Y is equal to 2x. X squared over 9 plus y squared over 4 equals to 1. And x squared plus y squared is equal to 1. Well, let's take each one at a time. The function y is equal to 2 times the absolute value of x may be indicative of a chevron syncline or the V-shaped valley of a young mountain stream. In the above equation, the vertex occurs at the origin of the diagram, and the slope is 2, which means that the ratio of the vertical drop to a given horizontal distance is 2 to 1. If you recall, V-shaped valleys are characteristic of young mountain streams with plenty of downcutting power and where the stream occupies the entire valley. In other words, no floodplain. Chevron folds have tight hinges and straight limbs. Chevron folds result from compressive stresses typically affecting a sequence of alternating beds of different competency and composition. In other words, different ductility contrast. In the sketch that I'm showing you here, I show you an angular unconformity, the red line, that separates a section of chevron folding from an overlying sequence of horizontal layers. Our second equation is y is equal to x squared. This is the equation of a parabola. The general equation of a parabola is y is equal to a times x minus h squared plus k, where h and k give us the coordinates of the vertex. A determines how wide or how narrow the parabola is, and the exponent, in this case 2, dictates how steeply the sides rise. What geological features could exhibit a concave upward parabolic shape? Well, more gently folded synclinal structures, also mature stream valleys with existing floodplains, as well as glacial valleys, for example. And this is a great photograph, if I may say so myself. This is a classic U-shaped glacial valley near Glacier Bay in Alaska. Our next equation is y is equal to 2x. Well, that's the equation of a line. The general equation of a line is y is equal to mx plus b, where m is the slope and b is the y-intercept. In our case, the slope is 2 and the y-intercept is 0. A linear equation of this type may be indicative of a normal fault where the angle between the horizontal minor principal stress and the fault itself is approximately 60 degrees or so. And here are some additional examples of normal faults in the Austin Chalk that approximate the linear function that we have discussed. What about the equation x squared over 9 plus y squared over 4 is equal to 1? Well, that's the equation of an ellipse that has a major axis length of 6 and a minor axis length of 4. Geologic features such as boudins may show you this type of general shape. Boudins are structures that are shaped like a sausage, or if you will, roughly elliptical structures formed by extension where a competent or rigid rock unit is stretched within a less competent or, if you will, a more ductile layer. You know, given the equation that I have presented for you here, I can tell you that elliptical boudins of similar proportions are described in Norway, where the competent rock, the boudin itself, is made up of amphibolite, and the more ductile strata are quartzitic schists. Our final equation is x squared plus y squared is equal to 1. Well, this is the equation of a circle with a radius of 1. Examples of geometric forms with circular cross-sectional shapes occur in geological features such as oolites or spherical grains formed by concentric layers. Oolites are typically composed of calcite or aragonite, in other words, calcium carbonate. The oolites form in warm, shallow, agitated marine waters. Oolites don't have to be made up of calcium carbonate. You can have oolites made up of phosphate, iron oxides like hematite and goethite, chert, and dolomite. The occurrence of quasi-spherical clastic sedimentary particles with circular cross-sections, particles ranging from sands to pebbles to cobbles to boulders, transported by streams and other erosional agents is also possible. Here you can see some rounded silicic cobbles, some which are quasi-elliptical or quasi-spherical. They indicate a long transport distance from the locality where the sediment originated. And as I said before, these clastic particles come in all sizes. Here you can see a quasi-elliptical granitic boulder at Cadillac Mountain in Bar Harbor, Maine. Well, I think it is interesting to notice how geological features approximate geometrical shapes. You're looking here at Le Petit Piton on the island of St. Lucia. This is a volcanic peak, and the geometric form of it as it now stands approximates the equation that I'm giving you there. By the way, the minus sign in front of the M being the slope, indicates that the vertex points upward rather than downward. Well, that's it. I hope you have learned something. Take care. Good luck.